guys, very exciting section, 5.2, the definite integral. In this section, we're going to start to connect the Riemann sums from 5.1 with limits, and then eventually it's going to go, of course, to derivatives once we get to 5.3. So we start to see the connection to our calculus concepts right here with the definite integral. Okay. Thinking back, where did we leave off in our conversation on Riemann sums? We said to approximate the definite integral, we will use rectangles of n subintervals. So the definite integral is the exact area between the function and the x-axis from your starting point to your ending point. So, well, where do we even begin with that, right? Let's just find some rectangles and we can kind of crudely get an approximation. When we did those Riemann sums, this is basically our approach. When I say the area here, I'm talking about the sum of the areas of all of these rectangles. So that area was approximately equal to, well, I should say when I say A, let me take that back. A is the exact area of that, that curved space. So A was approximately equal to the sum of the areas of the rectangles. How did we do that? We realized, hey, we can just add all of the heights together and multiply by the width. Since it's kind of like we're factoring out the width. Take the sum of the heights, multiply by the width. We can represent that with sigma notation, like so. Probably the easier thing to point out is the delta x. The delta x is the width of each rectangle. The summation here is the sum of all the heights. So we'll call it the summation from I equals 1 to n of f of x sub I. What does that mean? Well, in our example above in our drawing, n would equal 4, right? N subintervals. So we'd plug in 1, x1, x2, x3, x4, plug them into f, find the heights at each of these, add all of those heights together. So there you go. The summation from I equals 1 to n, f of x sub I would add all of your n heights together. You would then multiply that by the width. Okay, let's think for a second. What could we do if this is an approximation? What could we do to get the area, that curved area exactly? Is that possible? If we take more subintervals, right, that's going to be more accurate, right? So here I have 4, but if we made 8 rectangles, that would be more accurate than 4. If we did 16 rectangles, that'd be even more accurate. How many rectangles do we need to get that curved area exactly without any error? We're going to need infinitely many rectangles to do that because more is always better. Okay. So for the exact area, we're going to take n to infinity. So what does that mean? Well, we've got a limit, right? Now our area A is exactly equal to, same formula, but now take the limit as n approaches infinity. So the number of rectangles, the number of subintervals becomes infinite, and we will have that definite integral exactly right. We're going to do that, exactly that, in this section. One other thing I want to point out, this will be helpful later. If we have infinitely many rectangles, right, they're packing in here, they're infinitely tiny. What is happening to the width of each rectangle? Let's just mention that now. Well, if you get more and more, the widths get smaller and smaller, right? If you have infinitely many, then we'll say the width of each rectangle, it'd essentially be approaching 0. It would never equal 0, but those rectangles would become infinitely narrow. We get this tiny, tiny little, we'd call it an infinitesimal width, infinitely small, not zero, but infinitely small. Okay, just keep that in mind for a little bit later. Okay, wow. So we have this, this formula for how to get the area exactly. If we can just leave n as a variable and take the limit as n goes to infinity, we can get this definite integral perfectly. This is the definition of the definite integral. The definite integral of f of x from a to b is given by this. Notice we've got some new notation. Let's ignore what's on the left here just for a moment. There's our formula, the limit as n approaches infinity for the summation from I equals 1 to n, f of x sub I times delta x. Now that is really a beast right there. That's pretty intimidating, but we're going to use it pretty soon in a couple of examples. Okay, what's happening on the left side? This is our new notation for integrals. Okay, whenever there's a new concept, there's a new notation that goes with it. If you think back to when we finally saw the definition of the derivative, at that point, we also introduced a new notation for the derivative, the prime notation, f prime of x. We hadn't used that before. And the definition of the derivative used a limit, right? So now the definition of the definite integral, no surprise, uses a limit. The limits are the foundation of calculus. Okay. Well, what's going on with this notation? What a strange thing. It's like this kind of curved line here. That's weird. There's an a at the bottom, a b at the top. Then we note what the function is, and then next to it, look at that, the differential of x dx. Let's break that down, kind of explain what that notation means, where it comes from, and I think that will be helpful. That curved line, right, and when you see it typed out on the computer, it's a little different than when you write it by hand. Here it looks really fancy, it's like got these, fancy kind of, little circles, little balls, so like kind of like tassels or something at the end. And then it's like thicker in the middle, right? I mean, it's not going to be that way when you actually draw it by hand. And okay. That is the integral sign. Where does that come from? That is literally a stretched capital S. Why a stretched capital S? Because it represents a sum, right? We're doing a summation. Okay. What's up with the A and the B? When we write the integral sign with an A at the bottom and a B at the top, it means to sum the infinitely many rectangles starting from A, ending at B. Okay. So that's like telling us our starting and ending points go from here to here, from A to B. And it is a sum, and it's the sum of infinitely many rectangles. We're even like capturing the fact that it's a limit as n approaches infinity. It's like both of these pieces together are captured by that, the integral, and we would read that, the integral from A to B. What is the f of x? Well, the f of x gives the height of each rectangle. It's like the equivalent of the fxi. And the dx, well, we saw it before as the differential of x. The dx represents that infinitely small width, right? Dx is the width of each rectangle, but these rectangles are infinitely narrow. So we can't use delta x. Delta x would represent like, a finite value. But so we can't use a number because it's infinitely small. So we're going to use the differential of x to represent that infinitesimal width. There's an infinitesimal change in x from one side of the rectangle to the next. Infinitely small. Okay. So all of those three things together create our integral notation that we see right there. All righty, let's move on. We've got this theorem. The theorem says, kind of building on that, that notation and the definition of the definite integral. For, by the way, you would read this literally the way the definition said, the definite integral of f of x from a to b, given that it's equal to this, what would help us to actually perform, you know, the examples of the questions that we're going to see, perform these calculations? Well, it turns out, you know, we use this notation for now, but this is how we actually do the calculations. Delta x. We find the number for delta x with b minus a over n. We'll know what a and b are. And if we divide that by n, actually n is just going to be the variable n, because we're going to think later n goes to infinity, right? We did this same thing with Riemann sums when we found delta x. It was always the difference from the ending point to the starting point divided by the number of subintervals, b minus a over n. Okay. And the xi, we're going to need to know that. Xi is equal to our starting point a plus I times delta x. And what's that all about? When we set xi equal to a plus I delta x, we're thinking about it as using right endpoints. So take where it begins, but then think of the right side of that first region. So then we'll add on the width of that region. So for the first region, we would put in I equals 1. So it'd be a plus the width would get us to the right side. For the second region, I would equal 2. And so that would move us 2 delta x's over, and that would be the right endpoint for the second region, right? And so on. Okay. So how was this helpful at all? We're going to do these examples using our definition of the definite integral and using this theorem. We're going to do that in the next video.